14.5. Now we are calculating the pH of a weak acid solution. So weak acids are partially ionized in aqueous solutions. So because of that, this statement can no longer be found true. So now we need an equilibrium constant expression. This expression is going to be this is our acid dissociation constant. And this A here tells us that it's an acid dissociation. It's going to be equal to our hydrogen ion concentration times our conjugate base divided by the acid concentration. So the bigger that Ka is, the stronger the acid. If Ka is a lot bigger than 1, then we would know that the acid is completely ionized. So we'll have an example where our Ka is going to be given to us at 6.0 times 10 to the negative 6. Our acid concentration is going to be 0.30. So the only way, or maybe there's another way, and this is just the easiest way, is going to be to do an ice table. So we're going to write out our dissociation process. Over here, we'll have the ice. So to begin with, obviously our acid, we have the 0.30, and our products obviously would be zeros. So we're going to be losing x. There are no coefficients up here, so we can assume that they're all just going to be x's instead of maybe 2, 3x, whatever that would be in other equations. These are going to be plus x. So then down here for our equilibrium, it would be 0.30 minus x, and then these will just be x. So then we have our Ka. I'm going to write that out again. So then when we look here, we know these two are just going to be x squared. And down here we'll have the 0.30 minus x. But we're going to assume that this value is going to be much smaller than this value, so it'll be negligible. So then we'll just have x squared divided by 0.30. So now we have x squared equals Ka times our 0.30. So then we're going to have x is equal to the square root of our given Ka value we have up here, 6.0 times 10 to the negative 6 times our 0.30. So then, after calculations, we know that x will be equal to 0.0013. So we want to make sure that this x value is less than the acid concentration, which it appears to be, but we're going to make sure our percentage is low so that we can assume that our x is equal to our hydrogen ion concentration. So we'll take the 0.0013 divided by 0.30 times 100%, and we'll get 0.45%. So that's definitely a small enough percentage so that we can assume that X is equal to our hydrogen ion concentration, which will be equal to the 0.0013. So then we can plug it in to our pH, negative log. We'll plug that 0.0013 in here to get a pH of 2.87. And that is definitely an acid.